that means that it has topological order. So then I'm pretty much done.
Sorry,
Yes. Yes. Yes.
So how do our field is the gap in
No, thank you. I'm jumping ahead. So just the definition of the psi fermions. So what I wanted to do, you gave me, the vortex is in phi, okay? So I want to find some r with a constant h that will convert, convert the varying vortex in phi to a constant h. And so what I'm saying, the only r I can find has a branch cut as you go. There's no way to do it smoothly otherwise. So if there's a branch cut in r, it means there's a branch cut in psi. So psi is double valued, which is not acceptable. R is a single valued field. Everything has to be single valued. Another way to say it really is there's some gauge field in psi, and psi will actually experience some flux, and it'll be some high energy state. So that vortex will cost more energy than you would have thought. Anyway.
those sizes will be
Yes. The vortices will go. Yes. Yes.
You can't keep in that size.
Yes. Yeah. So in fact, if those vortices were present, then forget it. Why even work in psi? Work in C's. You'll in fact be back to the long ordered phase without topology. The trivial phase with a large Fermi surface. So, all right.
So what does oddness mean now? What is the R?
Okay. Yes. So this is easy. This is a very easy plane antiferromagnetism. In which case, I'd be talking about U1 gauge field, and then. But for SU2, then you have to think about hedgehogs, desuppression, and then you break SU2 down to U1. Or if you have SO3 Higgs field, then you can break it down to Z2. So these are the complications I didn't want to talk about. So the conclusion is, yes, you can get small Fermi surfaces, provided you have topological order. And the new language is that you get topological order if you have a gauge theory which has been Higgsed down to some smaller group. And this Higgsing is really associated with the suppression of certain defects in the antiferromagnetic order. All right. So that's the main message in my talk.
I'm really sorry.
Yes.
Answer again, but just to go back to the Lagrange's theorem.
Yeah.
I understand if you break the symmetry, maybe the unit cell.
Yes.
But here, if you look down to the language, what happened? How did you, was it that they
So, I mean, there's ways of, abstract ways of proving it through flux insertion and so on. Right? Here in this talk, I took a very pedestrian, practical point of view. That is, I imagine there's some fluctuating order, and I'm just trying to straighten it out. And if I straighten it out, I know I can reconstruct the Fermi surface. So in other words, what I'm trying to do is to get rid of the translational symmetry breaking, if you wish. Oh, sorry, no. If I have fluctuating order, then the translational symmetry has gone away. It's been fully restored. So I'm trying to straighten it out to imagine that there actually is translational symmetry breaking when there isn't. The order is fluctuating, and I'm straightening it out, and once I straighten it out, I've got a broken translational symmetry. And if I've done that, if I can succeed in doing that, then I will have succeeded in reconstructing the Fermi surface without breaking translational symmetry. Okay? So I was trying to do the impossible. But Lagrange's theorem would tell me you can't do that. And what this argument shows, actually, yes, you can do it. But you don't actually have to break translational symmetry. But you do have to pay a price. And the price is you've got to get rid of some defects. You've got to have the antiferromagnetic order. It can't be just totally random, in which case you'll have all sorts of defects. It has to somehow know that, have some topological coherence. in which only even vortices for the XY case appear, but not odd vortices. And then you can do it. So we found a loophole in Luttinger's theorem, if you wish, that you can have small Fermi surfaces without breaking translational symmetry. But we had to pay a price, and the price was the introduction of a topological order. So topological is a very useful thing. It allows you to do things that were otherwise prohibited, even in something that's very observable. So in fact, if you believe this theorem, which you certainly should, because we gave a fairly strong argument for it, now we can detect topological order. The way to detect topological order is just measure the volume of the Fermi surface. And if you find the wrong volume, you have topological order. Yeah. Yes, it could be. Yes. This transition. Yes. It's possible. Yeah, it's possible. Yeah. Yeah. Exactly. No. So there is a modified Luttinger theorem that is present and which protects both of them. Yeah. Yeah. I mean, there could be other scenarios, but there is a simplest scenario for this. Actually, we understand this quantum phase transition quite well. This is much harder. Then that's really the key problem for the high TC is to understand this one. Yeah. Yes, yeah. Good question, yes. Yeah. Well, so in photo emission, they would be broadened out, but in quantum oscillations, they would be still there. You would see them perfectly. Or if you form something called FL star, then you would see them in photo emission also. Yes. Okay, I guess I'm running out of time, right? So the final part was just connecting this to experiment and all right, so now finally I can, this is the phase diagram that puts everybody to sleep. This is the of the high temperature superconductor as a function of temperature and doping. But for my purposes, all I want to show you is that there's the antiferromagnet that I've talked about. There's the Fermi surface, the large Fermi surface. And then there's this pseudo gap. And notice that also these three AF, FL, and pseudo gap are arranged just like in my phase diagram. There's two phases and one on the top. and so, okay, I'm not sure. I could give a whole talk about all the different evidence that this is a system with a small Fermi surface. And okay, this is what the whole talk is about, just making this theoretical case. All right, so now I just want to flash this paper that's hopefully will appear in the archive in a week or so. Where what we did was we took this gauge theory, in fact, this specific SU2 gauge theory that I've pretty much outlined for you, and computed lots of properties. And then we compared them with computer numerical, the best state-of-the-art numerics on the Hubbard model, which is cluster dynamical mean field theory, and also quantum Monte Carlo. And it turns out, first of all, these numerics have been giving pretty good indication of some bizarre new type of metal. And they're not of sufficient resolution or a big enough system to actually see, any broken symmetry at lower temperatures, at least at this doping. So it seems like you're still in some metallic state, and we're trying to understand what it is. And so the bottom line is that this simple SU2 gauge theory fits the numerical data surprisingly well. So this is work by Shivayu Chatterjee and Matthias Scheuer. So this is the charge on or the psi fermion Fermi surface. So we just take free fermions for psi, some Gaussian propagator for R, and then compute the electron spectral function. And So this is the electron spectral function, and you see the small Fermi surface. Or, it's kind of fuzzy because, in fact, the small Fermi surface is in the psi, not in the r's. The red line has to do with what are called zeros of the Green's function, so I won't say much more, but there have been many, many papers in the literature saying somehow the zeros of the Green's function are the fundamental object. We disagree completely, that they're not. What's fundamental is topological order. The zeros actually don't even exist. They're approximate zeros. So only if you take the real part is there a zero, not the imaginary part. Anyway, so forget that. So here's the small Fermi surface. It has a gap on the antinodes, that's this point, and is gapless along the nodes. And along the antinodes, the electron spectral function in the SU2 gauge theory and this cluster DMFT look pretty similar. So the one thing we have to do is to choose the value of the Higgs condensate to reproduce this gap. And then after that, we just do our theory and everything else is matched. So for example, the self-energy, the real and imaginary parts of the self-energy at two different values of the hopping matrix elements look very similar. There's this so-called Lifshitz transition between hole-like and electron-like Fermi surfaces. We reproduce that. And also, well, the whole, anyway, so there's a lot of technical details, and I guess I'm asking you to take my word that we are quite happy with how well this does, this very simple SU2 gauge theory of fluctuating antiferromagnetism with suppressed monopoles. In this case, since you have SU2, then what you're suppressing are instantons, or the hedgehogs in the antiferromagnetic order. Okay, so that's it. If you want to know more about that, I'm happy to say more. So basically, I've given you some simple models and a realistic model how you get quantum states with bulk topological order. I should mention this has nothing to do with topological insulators, which have no bulk topological order. What they have are protected edge states. And that's another definition of the world topological, unfortunately, which is different from this one. But anyway, so this is more like the fractional quantum Hall states. But the states I've described, none of them break time reversal. And especially when you're talking about metals, where you have lots and lots of low energy excitation. And then the topological order is qualitatively associated with defect suppression, but more precisely with the presence of unbroken gauge groups in a Higgs phase. That's really what topological order is about in every case I know. Well, so something like the theory of weak interactions. You have an SU2 gauge group. That's fully broken. So there is nothing topological about it. It's a trivial phase. So we say that the theory of weak interaction has an SU2 gauge group. The only invariant meaning of that is a very high energy. Because of asymptotic freedom, there are SU2 gauge bosons. At low energy, you don't really need the SU2 gauge theory to describe it. There's no analog of asymptotic freedom here. So if you have a gauge group and you break it completely and you don't have asymptotic freedom, then you haven't done anything. It's up to you whether you use it or not. But if you have a gauge group and you break it down to a discrete group usually, then there's topological order in the Higgs phase. and that's, I mean, there might be some exceptions to this, but I believe almost every case known can be described in this language. So, yes, it could be non-abelian for sure, but I just took the simplest cases of U1 and Z2, which are abelian. And what we're most excited about is that this really encouraging agreement with cluster DMFT, and so maybe a topological order has been sitting in front of our noses for a long time in this pseudo-gap phase for the last 20 plus years. But it's hard to really make a completely ironclad case because, of course, topological order is not so easy to detect. And other annoying things like superconductivity come in when you lower the temperature, which get rid of the Fermi surfaces. Okay, well, thank you very much.
There are some other ITC superconductors like the high-happening types,
Yeah,
which doesn't have any pseudo-gap.
correct. Yeah.
Are they fundamentally different from two-phase superconductors?
Yeah, so I would say that, great question. I mean, that's another reason for drawing the phase diagram like this. So the electron doped cuprates and the pnictides, all the evidence is this, they go directly like this. It's just the whole doped cuprates seem to be up here and they go via this route. So when you dope the electron dope, it seems to be below this point. You go this way directly, or you can go through that route. And that's another nice thing of this theory. They fit together in the same theory with minimal, yeah, they're all parts of different routes on this phase diagram. Yeah.
What would be an experimental test for this?
Yes, well, the experimental test would be detecting Fermi surfaces that are small without broken translational symmetry. Yes, but that would mean, so that's already been done if you wish over here, but then that's at a fairly high temperature. It's not ironclad. It could be, okay, you're at high temperature and there's some fluctuating order, why you want it to be topologic. Well, our recent comparison numerics already tells us that even to fit the numerics at the high temperature, it's impossible to do without introducing a model with topological order. But it's now the model which has topological order only at 0 temperature. Strictly speaking, only present at 0 temperature. So now there's some indication that low temperature and high magnetic fields in this region here, there seems to be a metal with no broken symmetry. Over here you get this density wave order, which then also complicates things. So you have to look in this regime here at very high magnetic fields. Now there is this experimental TIFR which